Right, welcome all. My name is Suresh, lecturer in ECE. I'm going to teach the subject that is electronic device and circuits. Today's topic is UJT characteristics. Today's first topic is UJT characteristics. In the previous video lesson, we have learned about the special semiconductor devices, that is varactor diode first, and then we have gone to the topic UJT, unijunction transistor. In the case of unijunction transistor, we have seen the construction and working of the UJT. Now we are going to learn about the characteristics. Right? Figure shows the curve between emitter voltage V and emitter current I of UJT at a constant VBB between the bases. This is known as emitter characteristics of UJT. Just please refer to the yesterday's lesson. In that, yes, this is the diagram. Please draw this diagram once again to understand it well. Please draw it on paper. The characteristics of this UJT are drawn with V on y-axis and I on x-axis with VBB as a constant. The following points may be noted from the characteristics. Observe the curve characteristics. These are the V versus I characteristics. In that, by observing this curve, it started from the negative x-axis and quickly rises to the peak value with the increase in the current. Right? From the first portion of this curve, we can see Vp increases by increasing the current Ip. That means Ve increased because of the increase in the current IE or vice versa, and both reaches to the maximum value, peak value. V peak is achieved at I peak. After that, if you observe, there is a sudden decrease in the value of voltage, but the current value increases. Right? Current value increase. This is an anomaly compared to the usual MIC, that is Ohm's law. Right? In the next portion, that is, you can see negative resistance region in the curve. That's why it is called negative resistance. Why? Because as the current increases, the voltage decreases. It is inversely proportional. So this is a negative resistance concept. In this region, in this particular region of this curve, UJT characteristics, the UJT experiences a negative resistance region. Then after that, it reaches to the valley band, IV and VV, current valley band and voltage valley band. Then after that, it again increases as voltage increase from the current. That represents a similar to the forward characteristics of a diode. The third portion, it's like saturation portion. Right? So the first region is called cutoff region. In that the current is almost negligible and it is negative. Right? Very small portion is there. Then afterward it reaches to the maximum value peak, and afterwards it enters into negative resistance region and reaches to the valley band, and afterwards it's again entered into saturation region. This is the typical characteristics of a UJT. Now see the theory part. The following points may be noted from the characteristics. That is, first the cutoff region. The region to the left of peak point is called cutoff region. In this region, the emitter voltage is below the peak point voltage and the emitter current is approximately 0. The UJT is in its off position in this region. So UJT is off position in this cutoff region and the voltage is below it and the current is almost 0, that is negative value. It is very small. That is next portion, next region in the curve, that is negative resistance region. The region between the peak point and the valley point is called negative resistance region. The region between the peak point and valley point is called negative resistance region. In this region, the emitter voltage decreases from VP to VV. In this region, the emitter voltage decreases from PP to V value, and the emitter current increases from I peak to IV. This is in fact the very important feature of UJT. The increase in emitter current is due to the decrease in the resistance RB1. So why there is an increase in the current, that means decrease in the resistance of RB1? Because of the flow of charge carriers, that is positive charge carriers, which are infused from the heavily doped P plus region to the N region, and they are attracted towards the B1 terminal because of the negative VBB terminal which is connected to B1. Right? Now moving on to the next region, that is saturation region. The region beyond the valley band, so the valley band is called saturation region. In this region, the device is in its on position. The emitter voltage remains almost constant with the increasing emitter current in the region. See, though the valley point, from the valley point, the current increases to heavily. IV2 will almost end of this line, but the increase in this voltage, that is VV2, almost negligible compared to this increase in current. The increase in voltage is negligible. It is saturated value. Voltage is saturated. It remains constant, almost constant, not a pure constant. So that's why it is called as saturation. So these are the typical characteristics of a UJT. The most important thing is the negative resistance of the UJT. Applications of UJT. So where can we use this UJT? In the previous lesson, with the introduction of the UJT, we have stated it as a unijunction transistor and is used in high frequency switching applications. That is from cutoff to onwards. It is the switching of states on to off or off to on. So UJT is used in a variety of circuit applications. Some of them are listed below. Relaxation oscillators are sawtooth generators. Sawtooth generators, that is oscillator, sawtooth oscillator. Over voltage detectors, sine wave generators, pulse generators, switching circuits, phase controlling circuits, timing and triggering circuits, voltage or current regulated power supplies RPS, triggering of thyristors, multivibrators, counters, etc. So these are all the circuits in which the UJT is used, the typical application of UJT. Some of them you are going to learn in the coming semesters. Now moving on to the next special semiconductor, that is photodiode. We know diode, but what do you mean by photodiode? Photo means light here. Okay. The photodiode is a two-terminal PN junction device which operates in a reverse bias. It should be operated in reverse bias. if you want the photo effect, that is the light effect. A photodiode differs from a rectifier diode, that is normal diode, in a sense that its reverse current increases with the light intensity at the PN junction. See, read it again. A photodiode differs from a rectifier diode, that is a normal diode, in a sense that its reverse current increases with the light intensity at the PN junction. Generally, in a normal diode, if you remember the VI characteristics of a normal diode, there in the positive, that is right. If you remember the VI characteristics of a normal diode, in the first quadrant, that is in forward bias of this diode, we have um, exponential relation with the voltage. The current increases exponentially with voltage. Then in the reverse bias section, we have a reverse leakage current of small value, which is of the order of nano-ohms, and it reaches to a constant value. After that, as the voltage, reverse bias voltage increases, it reaches to a point where the diode breaks down. So that is a normal diode. But in this particular photodiode, as the photo, that is the light, is applied, it is made to concentrate on a PN junction. In a junction, then when the diode is reverse biased, right, these two conditions, when the diode is reverse biased and the light is made to incident on a PN junction, then the current, which is actually a reverse leakage current, saturation current of small value, increases in this particular photodiode. So it conducts in the reverse bias. Photodiode conducts in the reverse bias. So reading the third point, when operated in reverse bias, the photodiode works as photoconductive cell, and with no bias, it acts as photovoltaic cell. See the difference photoconductive and photovoltaic you are going to learn in the next slide, the coming slides. Okay. When operated in reverse bias, when we apply the reverse bias, diode works as a photoconductive cell, that is, it allows the current to flow. And with no bias, it acts as photovoltaic cell, that is, it stores the energy, it stores the voltage. It will store the voltage and give it to the battery, the chargeable battery. It is connected to the, that is like a solar cell. That is exact the meaning of solar cell. That's how the solar works. When the solar intensity made to point on a photovoltaic cell, and the cell, because of that light intensity, there is a flow of charge carriers, and this will be connected to the DC battery, which will store this energy, whatever the voltage generated because of that solar energy. But in the case of photodiode, in the reverse bias, the voltage we apply, if we apply the voltage and the light intensity made to point on a junction, then it will function as a photoconductive cell. That current will flow in the diode in the reverse bias because of the applied voltage and the light intensity. But in case of photovoltaic cell, that is solar cell, only we apply the light intensity, that is the natural sunlight. We don't apply any reverse bias there. In that case, the charge carriers will be flown across this diode because of the light intensity, and the current whatever is produced is stored in a battery, external battery. So that's how it will generate the power. Now see the diagram of the whatever photodiode we are looking into. See, it is a PN junction, and we have extra a plastic case covered around this PN junction, and the incident radiation is made to fall on a lens. Lens will concentrate the light to be made to radiate at the PN junction, and the circuit, whatever the PN junction, is connected to a VR, reverse bias, because the positive terminal is connected to the negative and negative terminal is connected to the P type semiconductor, and there is a load resistor. And if you see the symbol, circuit symbol of this photodiode is similar to a diode but with extra light symbols, that is arrows that represents the light which are following on the diode. So that is a symbol and this is the actual circuit. Now see the construction. Figure A and B shows the, please draw the circuit, please draw the circuit. Compulsory you must draw the circuit and symbols in order to remember, because there is 10 to 12 special semiconductor devices which we are going to learn in this chapter, so one must write it completely. Figure A and B shows the structure and schematic symbol of a photodiode. The photodiode is made up of semiconductor PN junction. It is kept in a sealed plastic or glass casing. The cover is so designed that the light rays are allowed to fall on one surface across the junction. The remaining sides of the casing are painted to restrict the penetration of light rays. So that's how it should be made. The plastic case is made to allow the light only on one side, and remaining all the other cases, other sides must be restrict this light rays. As seen, a lens has been used in the cap of the unit to focus maximum light on the reverse bias junction. The active diameter of these devices is about 2.5 mm, but they are mounted in standard TO5 packages with a window to allow maximum incident light. So these are the technical specifications, because of the diameter, how much you will have an idea. It's about 2.5 mm. Very little, because the diode itself is very small. So on that we have to allow this cap. You would have already seen this LEDs, actually photodiodes like things in your personal life, right? The size also you can compare. Now see the operation. The basic biasing arrangement of a photodiode is shown in figure. We know that a rectifier diode has a very small reverse current when it is reverse bias. Here rectifier diode means normal diode, because in the rectification application we should use only the normal diode, because rectification will happen when it will not allow the current to flow when it is reverse bias. Yes, it will allow the current to flow when it is forward bias. That is called rectification. That's a normal diode function. But in case of photodiode, we are using it in reverse bias mode and it is conducting. It is allowing the current to flow in the case of reverse bias. That's a normal diode will not do that work. So here onwards, if we use the rectified diode, means it's a normal diode. Reading the third point, the reverse current increases with the temperature due to an increase in the number of electron hole pairs. Why? Because when the light is incident, light is made to incident on the junction. In the junction we will have the depletion layer, that is immovable ion, that is holes and electrons, that is the magnetic carrier charges, and there are immovable ions. When heat, that is the light, is made to concentrate on the thin junction, the heat is produced. Because of light, the heat is produced. Because of that heat, the bonds between these holes and electrons will break. Because of the applied heat, the bonds between these holes and electrons will break, so they produce the electron hole pair. So each one electron which is generated, each one electron which is produces a free electron besides the hole. So it's a hole electron pair. So when there is no incident light, the reverse current is almost negligible and it is called the dark current. When there is no incident light, it will act as a normal diode. Then the reverse current, a small value of reverse leakage current will flow. This is called dark current because there is no incident light. When light falls on the reverse bias PN junction diode, additional electron hole pairs are generated. The movement of these electron hole pairs in a properly corrected circuit results in a current flow. The magnitude of photocurrent depends on the number of charge carriers generated and hence on the illumination of the diode element. So how much is the light intensity you are making it to point at the junction will result in the current that is to be flown in this diode when it is reverse bias. So the light intensity is directly proportional to the current generated. This current is also affected by the frequency of the light falling on the junction of the photodiode. So frequency, actually the frequency means it is directly proportional to the power, energy that is of the light. And you know in the light we have different colors depending on the frequency. It is the wavelength which can be calculated from frequency. So which will have different energies. Because of the different frequencies we have different energies. So whatever the energy that the light will have, it will produce different heat. Okay, because of that the electron hole pairs depends on the amount of heat it produces. If the lesser heat is produced, there is lesser number of electron hole pairs. There is more energy and more electron hole pairs will be generated. So if you want to see the characteristics, observe the curve. The curves we drawn on the third quadrant, that is the reverse bias characteristics, where we have to draw the, in case of normal diode, they have drawn the characteristics of this photodiode, where it will be working in the reverse bias condition, right? But we have drawn number of curves because of the change in the illumination, intensity of illumination, 0 lumens per meter square, 1000 lumens per meter square. That is how much light intensity is falling on a particular 1 meter square area. As the energy increases, as the luminescence increases, luminescence value increases, the current produced, reverse current produced is also increasing. Observe the curve increasing in the reverse direction and reverse direction, that is the negative value. So figure shows the characteristics. You should draw, yes, one must draw the characteristics. Please draw it by pausing this video. Figure shows the characteristics curves of a typical photodiode. A study of these curves reveals in the following facts. The reverse current increased in direct proportion to the level of illumination, as we have already discussed. Even when no light is applied, there is a minimum reverse leakage current called dark current flowing through the device. Germanium has a higher dark current than silicon, but it also has a higher level of reverse current. The dark current for this particular device is approximately 25 microamps at a reverse bias voltage of 3 volts. Therefore, resistance of the device with an incident light, so R reverse is equal to voltage by this current. V is equal to IR, so R is equal to V by I, right? Voltage 3 by reverse current 25 micro 10 power minus 6. So we'll have final value 120 kilo reverse resistance. At 20,000 lumens per meter square, the current is approximately 300 microamps, and at 3 volt, these are the typical values, practical values. The resistance under this condition is 3 by 300 into 10 power minus 6 will result in 10 kilo ohm. So the reverse resistance is 120 kilo ohm when it is dark current 25 microohms, right? And there is no illumination. Dark current is approximately 25 microohms with a reverse voltage of 3 volts. Then we have 120 kilo ohms of resistance. But when there is an incident light of 20,000 lumens per meter square, then approximately 300 microamps current flown in that diode, then the resistance has decreased. The resistance decreases to 10 kilo ohm, 120 kilo ohm to 10 kilo ohm, that is almost 10 times decrease. These calculations show that the photodiode can be used as variable resistance device controlled by light intensity. This is the very useful application of this particular diode, right? We can use it to variable resistance because the resistance is varying 120 kilo ohm to 10 kilo ohm because of the applied incident light. When there is no light, zero light, it is 120 kilo ohm. When there is 20,000 ohm, that is the maximum value or some typical value. So we can take the value in between 1000 lumens, 1500, 2000, 2500, 10,000, 700. So we get the values of resistance with some like 120 to 100, 80, 90, or 60, 50, like that. So because of the applied light intensity, the resistance, reverse resistance is changing. So that is a variable resistance device controlled by light intensity. So that is the special semiconductor device, that is a photodiode, where it should function in a reverse condition, and the current, the photo light intensity has to be made to produce at the junction itself, made to be incidented, made to be falling on the junction of, in case in the reverse bias mode. Now moving on to the next special semiconductor device, that is phototransistor. It is similar to this photodiode but with the 3 terminals. The current developed by a photodiode is very low because it is in microamps, right? This current cannot be used directly in control applications but must be amplified. After amplifications, the photocurrent may be high enough to be used in a control system. For example, to set a relay. To set a relay, we need a photocurrent of higher order value. So that's why we need the whatever the current it is produced in the photodiode, it should be amplified. The phototransistor is a light detector which combines a photodiode and a transistor amplifier. Read this line again. Phototransistor is a light detector. When the light falls, it will conduct, so there is a detection of light. When there is no light, it will be in off condition. So that's how it will be off and on because of the incidental light, which combines a photodiode and a transistor amplifier. First see the diagram. Draw the diagram carefully. Everybody must please draw the diagram on a paper. After drawing the diagram, please observe the diagram, and inside we have the symbol of the phototransistor also, that is normal transistor with the incident light arrow symbols that represents the light. It is a NPN transistor with emitter junction, collector junction, and the radiation through lens is made to fall on the base P, and the emitter collector are connected to the external voltage VCC DC voltage. N is connected to the negative, and collector N is connected to this collector, and it is enclosed in a plastic capsule. See the construction. Figure A shows an NPN phototransistor which is generally used in common emitter configuration. Generally, figure shows the NPN phototransistor, which is generally used in a common electric application. The base of the bias voltage is applied between the intercollector junctions. The base left open, right? The base is not connected to anything. The base is left open, but the emitter and collector are connected to the bias voltage VCC. The construction of phototransistor is just like a conventional semiconductor NPN transistor with a little hole made on the surface near the collector base junction. It is made to fall on collector base junction. See the diagram. JC on JC. Small lens is fixed on this hole for allowing a focused light beam. Small lens is fixed on that hole for allowing a focused light beam to concentrate on the collector base junction. Small lens is fixed on this hole for allowing a focused light beam to concentrate on the collector base junction. In the modern methods of fabrication, highly light effective materials are used instead of making a hole and fixing a lens on it. A phototransistor is similar to an ordinary transistor except that no base terminal is provided. So base is left open and it is enclosed in the plastic itself, so it is not available to connection. Instead of a base current, the input to the transistor is provided in the form of light. So in the common emitter configuration, if you can remember, the emitter is made common and the input is given to the base. So the base current, which is the most important thing in the transistor amplifier in the CE configuration, that is base current will make the transistor on and it will produce the amplification. I is called beta IB something, right? But in this case, the IB is 0, base current is 0 because of the external voltage we are not applying, but IB current is generating because of the light intensity. So instead of base current, the input to the transistor is provided in the form of light. It works on the same principle of photodiode. So if you remember, if you remove one terminal from the transistor, it will work as a similar to a diode. So the operation from the figure, it is clear that the emitter base junction EJ junction JE is forward bias, whereas the collector base junction is reverse bias. So see the JE emitter junction, N terminal is connected to negative and the P, that is positive terminal, is connected to the base, which is left open, so it is almost 0, right? So when the negative is connected to the negative terminal and P is becomes 0, it will be in forward bias. Very good. Next, the JC collector junction, N terminal is connected to the positive of VCC and the P is left open, that is considered as a 0. Then N is connected to positive and P is connected to 0. So the relative voltage will reverse bias this collector junction. So with this thing, the JE is forward bias and JC is reverse bias, which is the required condition for the amplifier mode of application of a transistor. That is, emitter junction has to be forward bias, collector junction has to be reverse bias. That is happening here. And when the transistor is kept in darkness, there will be a very few minority charge carriers, that is thermally generated, which will cause the flow of reverse saturation collector current. So when it is in darkness, that is no current, no input current, no input light, that is no light, no heat, no electron hole pair and no current. Then there is a small reverse leakage, current saturation current will flow. This current for obvious reasons will be negligibly small. It is also called dark current. On light being focused at the collector base junction, additional photo generated minority charge carriers will be available, which will add to the reverse saturation current. So the light is made to radiate or concentrate on the JC collector junction. On light being focused at the collector base junction, additional photo generator minority charge carriers will be available, which will add to the reverse saturation. Thus, as soon as the light source is applied, the transistor starts conducting and amplified current starts flowing through the reverse biased junction. Thus, as soon as the light source is applied, the transistor starts conducting and amplified current starts flowing through the reverse biased junction. So that's how the phototransistor will function. Now look at the characteristics. Typical collector characteristics curve, IC versus VCE. We are drawing IC versus VCE, which are the collector characteristics of a phototransistor as shown. This curve depicts the variation of collector current with collector emitter voltage for various values of illumination, which is expressed in units of lumen per meter square or lux. These curves depict the variation of collector IC versus collector emitter voltage VCE for various values of illumination, for variation of light intensity. When there is zero lux, that is dark current, there is small reverse leakage current and milliamps will flow. With the increase in the luminescence 300 and 600, right, the curve slope changes, right? And with the increase in VCE, there is a huge increase in the IC and the starting portions, and after that it is just to the maximum value, that is the saturation value. The study of these curves reveal the following facts. The current in a phototransistor is dependent mainly on the intensity of light entering the lens. See, though it is increase in the VCE, observe the curves. With the zero luminescence, though there is an increase from 0 to 10, the VCE, but the current IC for the 0 lux curve is small. But for the 300 lux curve, it is around 1. And but for 600 lux curve, luminescence curve, 0 to 10 will produce 2. That is almost 50% and doubles. With the illumination increasing, the current will double, increases rapidly. It depends mainly on the light intensity only, not the applied voltage. The photocurrent is less affected by the voltage applied to the external circuit. Now we see the next topic, that is photovoltaic cell. The photovoltaic effect is the creation of voltage or electric current in a material upon exposure to light, and is a physical and chemical property or phenomena. Photovoltaic, because of the light, we are producing the voltage or electric current in a material without applying any of the external voltage here. The photovoltaic effect is closely related to the photovoltaic effect. In either case, light is absorbed, causing excitation of an electron or other charge carrier to a higher energy state. Excitation of electron or other charge carrier to a high energy state also happen. The main distinction is that the term photoelectric effect is now usually used when the electron is ejected out of the material, usually into a vacuum, and photovoltaic effect used when the excited charge carrier is still contained within the material. These all definitions remains the same because Because of the light intensity, if there is a production of current or voltage, that will be seen as a photovoltaic effect. In either case, an electron potential, that is voltage, is produced by the separation of charges, and the light has to have a sufficient energy to overcome the potential barrier for excitation. For that excitation, for the production of free charge carriers, for the breakage of the bonds, the light has the energy. We know that energy is sufficient to break these particular bonds, because of the excitation requires the absorption of heat, absorption of energy by the electron or by the charge. The physical essence of the difference is usually that photoelectric emission separates the charges by ballistic conduction, and photovoltaic emission separates them by diffusion. But some hot carrier photovoltaic device concepts blur even this line of distinction. So this line of distinction we don't need it actually. It's considered as directly the production of voltage or current because of the light intensity without applying any external voltage. Application of photodiode, photo detection systems, demarcation circuits, logic circuits, optical communication, high speed reading of punched cards and tapes, reading of film soundtrack, production line counting of objects, and photo transistors, measuring device, relay circuits, photometric applications for measuring intensity of light, for detection of light, and so on. In control applications as a light operator switch, as actuators in the photo relay circuits. Applications of photovoltaic cells in automatic exposure controllers, in research in satellite and space vehicles to supply power to electronic and other equipments or to charge storage batteries. In many applications like solar calculators, solar cookers, solar water heaters, solar pump sets, solar lights, etc. In microwave repeater stations, TV transmitters, in solar power stations to generate electric power. In aerospace projects in laboratory. So these are the today's topics we have learned about, that is photodiode. First we have seen the construction and circuit diagram and circuit symbol and the characteristics of photodiode. You must remember that photodiode is operated in reverse bias condition. Next, the phototransistor, because the current generated by that photodiode is very less, it is not useful that much, but it has to be amplified in order to use in the relay circuits, which should control the higher voltages, control applications. So we need to design the phototransistor similar to the photodiode. It is also designed, but the base terminal, main base terminal, is not connected to anything. It is left open, right? It is in C configuration, and the junction, emitter junction and collector junction are made forward bias and reverse bias respectively. So in order to function the transistor in a amplification mode, that's how the whatever the current is generated will be amplified, and it is similar to the photodiode application also. Next we have moved to the photovoltaic effect, which is similar to photoconductive cell, that is a phototransistor, but with a small difference, we don't apply external voltage here. Whatever the light intensity is made to produce it to incident on the junction will produce the current or voltage, and that will be stored in the external batteries. And we have seen the applications of all these photodiode, phototransistor and photovoltaic cells. So please read this all the special semiconductor devices carefully, because most of the questions of the competitive exams will be asked on these topics only. You may easily get confused because there are number of special devices. Each and every point is important, and please read the standard textbooks for extra knowledge and practice the questions. Do the virtual labs itself. It will be simple circuits, because very simple components and resistors and input signals required. That's it. DC batteries only, no frequency response curves have to be drawn, just the DC multimeter if you place on the across the diode or transistor for the voltage and the current. Just take the values and draw the graph. You will see the curves. So with this, I am going to conclude today session. If you have any doubts, please mail me at sureshakul2001@gmail.com. And tomorrow we are going to learn remaining special semiconductor device, which are the fifth chapter of this subject. Please read all these previous lectures, because in order to understand the further devices you need the knowledge of these devices. Thank you. I'm closing the today's lesson.